we have been talking about inductance. It's a very important property of magnetic materials. And in this example, we're going to calculate the inductance per length of a solenoid. And a solenoid is an important circuit element, if you will, if you want to call it that. And a solenoid is this thing that's got a lot of turns, okay? And each turn is a circle, right? And we're saying it's infinitely long, and all that means is that this length is much larger than, the radius, if you want to call the radius A. And we'll say that it has an axis like this. So we'll call this AN. AN is normal to the circular cross-section there. Alright, so we're going to calculate the self-inductance, and we've already calculated the flux density of this thing previously, and we calculated it as mu times I times N times AN. I've already said what AN is. Mu is the permeability, of course. I is the amount of current that each coil has, and N is the turn density. N was this capital N, which is the number of turns, number of coils, divided by the length of this thing. Okay, so we calculated this previously, and we're going to use that here. Alright, so what I need to calculate the inductance is the flux through each coil. Alright, so that's easily done actually in this case. So what we're going to do is we're going to consider the surface S to be the surface of one coil. So we're going to integrate over the surface of the flux density dotted with the surface vector. So this integral is easy to do here because the flux density is in this AN direction, but so is S. So they're parallel. So when you do the dot product, you just get B times S, B times ds, and then when you integrate over that, you just get B times S, like that. Okay, now, so that's the flux through each coil, okay? And we want the flux linkage, which we're calling lambda. And so if the flux through each coil is B times S, then the flux linkage then is N times B times S, because again we have N of those coils. Alright, so now what we showed was that the inductance was, I guess we defined it as lambda over I, okay? But I want the inductance per length of this thing, so I'm going to divide both of those sides by the length of the solenoid L, like this. And so I'll just put N times B times S in for the flux linkage, like this. And I'll notice that here's that ratio again, capital N over L, that's this thing here, that's the turn density, right? So this is N times B times S over I, and we know that the magnitude of B is mu times I times N, right? We did that previously. So I've got N times mu times I times N times the area, the surface area, and the surface area I'll just call pi A squared, right? The radius of this thing is A divided by I. So the i's cancel, I've got N squared there, and so I get the inductance per length of this thing is N squared times the permeability times pi times A squared. Got it.